All right. So first, I wanted to acknowledge that this short course is sponsored in part by the CCS in Community Engagement Program. And we want to thank them for supporting travel to the upcoming supercomputing meeting in November. And there's still a lot of opportunities to engage with this program. And so if you're interested in going to SC23, there's different levels and tiers of projects that you can do in order to get funding for travel. And they're very supportive. So I highly recommend taking a look at this program. All right, so just a brief outline. We're first going to go over accessing ACES. Everybody should have an account and been set up on our training allocation for our new ACES cluster. We're going to show you how to launch RStudio on as an interactive app through our Open On Demand portal. And once we do that, we'll open up a workbook that I've created using a few different packages in R to go over some of the fundamentals of the R programming language. So this will include just using R as a basic calculator and using some built-in math functions. Then we'll move on to data types, variables, and then some things like vectors, matrices, data frames, how to import and export data. And then finally, we'll go into some data visualization, specifically using a package called ggplot2, which is a widely used plotting package in R. All right, so these are the steps now to go through and log on to our system. So if you go to hprc.tamu.edu and click on the portal drop-down menu, and then select ACES portal access, you'll need to select the correct login information for access and log in using your access credentials. Once you are there, we can open up RStudio. All right, so once you are at our portal, you can click on Interactive Apps and then go down to RStudio. And that will bring up this screen here. So you can set your number of hours here to 7. That should cover the length of the course today. We'll only need to use a single core. We won't be using that much memory, so you can set it to 5, 10, 12 is fine. We won't be using a lot of memory today. Once you have all of those set, you'll need to click on the launch button, and that'll bring up a screen that looks like this. It will take a few minutes for your session to initialize and become ready. And once it does, you'll see a Connect to RStudio server button, and you can click on that, and it should take you to an RStudio screen. So I'm going to go ahead and do these steps myself. All right, so I'm at the ACES portal, interactive apps, RStudio. All right, so 7 hours looks good. 1, 12, that's fine. I'll click launch. All right. Okay, so it should bring up a screen that looks like this. We'll go back and go over this a little bit. So we have a few different views here. The first tab on the upper left says console, and this is the R console, which allows you to input R commands directly. We also have access to the shell through the terminal tab. So you can use that like you would if you were to say like SSH into our system or the node that we're on. Over here is where you'll see a lot of different helpful tabs. We have a file browser that allows you to go through and look at where you are and the different files that are available, allows you to interact with the file system of the machine that you're on. Whenever we get to the end of the day with our plots, this is where they'll be shown in the plots tab. Packages allows us to load and install packages from this GUI interface. And this is one of the things that makes R very powerful, is the number of packages that are available, specifically things like discipline-specific packages. So I come from a life sciences background, and there are a lot of packages that were built by like biologists to complete certain tasks, and they really extend the functionality of R. And that's why it remains one of the more popular languages among researchers. And finally here, what I want to cover is this help section right here, and it allows you to look up things like commands and functions, or help with packages and things like that. All right, so to access the course materials, what you'll want to do is click over to the Terminal tab in the RStudio. Show you real quick. So make sure we click right here. You should have a prompt like this, and then you can copy the materials to your current directory using cp-r /scratch/training ACES _ fundamentals of R programming. Then we'll do a space and a period, and that should copy all of that material here. And if we do ls, we can see now, among other things in my home directory, I have this ACES fundamentals of R programming directory. So I can change my directory to that using the cd command. And if I list the contents again, it shows I have this ACES fundamentals of R.rmd worksheet and the kinghouse data.csv. So if is there a way I can copy the code? So once you have this in your home directory, so I'm not sure how to say your name, Gogol. Once you have this in your home directory, then you have access to the code for as long as you have an ACES account. You can also just download it directly. So if we go back to the Open On Demand portal, and you go to Files, Home Directory, you should be able to see the directory that we just copied. All right, and so hopefully they can help you get that sorted out, where you can share your screen so they can see what's going on. If you have run the command correctly, you should have two files, the ACES fundamentals of R.rmd, and then this kinghouse data.csv file. All right. So if we have those, is anybody else having an issue? Or can we go on to opening the notebook now? All right. So now what we need to do is we can just go to File, Open File, and you should see this ACES _ fundamentals of R programming here. Double click that, and then select the ACES _ fundamentals of R.rmd file, and click Open. All right, so that's going to bring up all of the code that was used to generate the program or the workbook. And so you should all have access to this and now a copy of this to use in the future if you'd like. Once you have this loaded, we can just click Run Document right here. All right, and you may have this pop-up blocked error. Just hit Try Again. And it should open up a notebook that looks like this. All right, Google, there's a breakout room If you want to join that, there's some HPRC members in there that can help you get the files copied over so you can get to this point. All right, so has everybody been able to open up this notebook? Okay, so this was the most all right, the probably technical difficulty laden part of the day. So if we're here, then we should be good to go. So this is the workbook. And you can see on the left, we have like a table of contents here. So we start off with R as a calculator. All right. So this is what we'll be working through today. If you have RStudio installed on your system or on your local computer, you can download this and you'll need to install the packages that are required, but it should run on your local computer or it can run on any system that has RStudio or R installed. And it will launch this workbook, which you can go through and do these topics at any time. If you need a refresher or if we don't get to something today, you can go back in and click on the topic and run through the material again. So for example, there's some bonus material down here on things like flow control, so for loops and while loops, which we won't cover today, and then how to make user-created functions. So I just included that as extra material in case you want to reference it in the future. So we're going to start off, though, with just R as a calculator, because in its simplest form, R is really a language designed to do statistical analyses and mathematical functions. So that's how we'll start off using it. In order to do that, we need to know the correct arithmetic operators. And they are very similar to what you would find in many other programming languages. Addition is the plus symbol, subtraction dash, multiplication is the asterisk, division is the forward slash. For exponents, we use the hat, and then to get the remainder after division, the modulo, it's just 2% symbols. And so to run code here, we'll just click on these code boxes. So it's similar to like Google Colab or a Jupyter notebook. And then we can just type in what we want. So 12 plus 3 and run code, and we get 15. All right, so to subtract 7 from 11, 11 minus 7. Oh, excuse me, hit a wrong button there. All right, 11 minus 7 and run code, and we get 4. So we'll go through all of these. 27 times 9, again, is the star, the asterisk. Divide 46 by 8. That's not going to be clean. 5.75. All right. 11 to the third power. We'll use up caret or the hat. Okay. And then finally, to find the remainder or the modulo of 11 divided by 3, it is 2% symbols. All right, so pretty straightforward and easy to use. The great thing about R is that there are a lot of built-in functions, and some of those are numeric functions. So we've got a table here of these kind of higher order mathematic functions, so like getting the mean or the mode, the absolute value, square root, some trigonometry functions, and then built-in pi and infinity here at the bottom. So we can use these functions just by calling them. So we'll do, to calculate the square root of 10,000, we just need to do call square root, open parentheses, and then put in our number. All right. get the exponential value of -1. Again, we'll just do exp. And you can see these suggested functions start to pop up, which is nice. And then we'll do -1. And then finally, to get a sine of pi divided by 2, we'll just use the sin function here. Pi divided by 2. All right, so for some of these statistical operations, we'll need to provide a vector, which is essentially in R is kind of a list of elements that are all of the same data type, which we'll cover in a few topics. But we've already created an object called X for you here. And so to calculate the mean of that object, we would just type in mean X. All right, 5.5. To do the median, we would do median X. Again, 5.5. Standard deviation, we go back and look, it's just SD. We have a standard deviation of 3.027. And then the sum is 55. And then to get the maximum value, we just run max and 10. All right, so in that list, we can see by just typing in X. So that was a vector of numbers going from 1 to 10 that we did all of those calculations on. All right, perfect. Yeah. So that shouldn't take too long to install the packages. Learn R has quite a few dependencies, but many of those should already be installed. All right, so it is taking too long. All right. Yeah, sometimes if we install like a fresh R on our system, it can take several hours because of all the packages that we need to install. So maybe there were quite a bit more than dependencies than what we had to install. All right, so let's move on to the next topic, data types. We're going to be talking about essentially 4 different data types in R. We have logical data types, so that's binary values of 0 or 1, or logical values of true and false. And these are case sensitive in R, so you can do either a capital T or capital F for true or false, respectively, or all caps true or all caps false. We have numeric data types, which are general real numbers, including both integers and decimal numbers. Then we also have an integer-specific data type. And this is a little odd in R. To specify integers, we have to type the number followed by a capital L. And then finally, we have character data, which is just strings of letters and other characters. So similar to something like Python. So here we have learning R, or just C++, and those are going to be denoted in singular or double quotes. There are a few built-in functions to check data types. There is the str or structure function and the class function. So in order to use these functions, we just type out the function name like we did with like mean or median, and then put in the data that we are interested in checking. So here we're using class to show what type of data 10.5 is. So if we run code, it's numeric data. The str structure function tells you the type, and it also prints off the data itself. So if we run this again with the structure, we see it's numeric, and then it prints out 10.5. All right, so you can use this code chunk here to check these variables right here. I'll give you a few minutes to do that in this independent exercise. All right, so we can look at this now. Let's just do class here. Class 1, 2, 3, and run code. It's numeric. If we put it in quotes, though, it turns it into character data. All right. 12L, again, that weird notation for integers. We do just a capital T, that's logical data. But if we're doing lowercase true, object true not found. All right, so true should be all caps true, right? So what is it looking for here? Does anybody know? If we type in all lowercase true without any quotes.
Guess a variable called true.
Yeah, exactly. So it's for a variable here called true, which we'll discuss in the next topic. So it's unable to find that because we haven't created that variable yet. And if we do true in quotes, now that is character data. All right, Google, your notebook is open now?
Sorry, yes, it is. So I have the 2 files here.
All right, so we're in data types now.
Okay.
All right, we can also use the is.type functions to check whether or not certain data is either logical, numeric, integer, character. And that's just is dot and then the data type. Yes.
Sorry, I have a quick question. So where can I access this? The page that's open now for you?
If you go over to the left and select data types.
No, I cannot access that. I cannot see that folder. So
Did
mine
you
is still in the console?
Oh, did you click on run document?
No, I have not. No.
Yeah, click on run document.
Okay.
And you may get an error, and that if you have pop-ups blocked, and you can just click try again, and it'll open.
Should I just run all of it?
Yeah, just click run document all of it, and it'll bring up this interface here. So it's not run, it's a green triangle. Can you see my screen?
Yes, I can.
So right here where it says run document.
So, okay,
You'll
so
click
do I
on
need
that.
to click anything in particular, or just like
No, just hit that and it should run. And it may take a few seconds, but then it should try to pop up in a new window.
So do I have to like click the files, one of the files from there, or just like literally write run in the terminal or something? Or
No, you just click this button that says run document. If you've opened up if you have this open, the ACES _ fundamentals of R, did you open that file in?
Yep, I
R
opened
Studio?
it, and yep, and I can see it says like title, output, author, runtime. Like
Okay. Then above that, it should just say run document with a tiny green arrow that's pointing to the right.
Is the second line, should I click the second line and run it, or?
You don't have this button right here that says run document.
Yes, I do have it. Yeah.
Yeah, just click that. Just click that and you should be good to go.
Oh,
It should
okay.
start.
Oh, got it. Okay, so my pop-up is blocking it. I'm gonna.
And then try again.
Yep, I can see it now. Thank
All
you.
right, great.
Sorry for that.
No worries. No, that's this. Once you get past this part, everything else should be straightforward. We shouldn't have any technical difficulties. I say, cursing myself. All right. So the is type functions, we'll run this, and it will provide Boolean output for whether or not what you have in between these parentheses is that data type or not. So true here is a logical data type. It's not numeric, an integer or character. So our output is true, false, false, and false. All right, so take a minute or two and run this independent exercise. Check and see if 4.70 is numeric type, if U is character type, and T is logical type. All right. So this one's really straightforward and easy, this independent exercise, but I did want to take the opportunity here to point this out if you haven't seen it. For all of these exercises, we have a solution coded in. And so if you get stuck on something that's a little more difficult later on, you can just click solution and it'll pop up and you can copy it to your keyboard and paste that in here. All right, so the last exercise in this independent exercise is checking to see if this integer 6L is numeric. So let's see, 6L. All right, that's true. So it is numeric data, which makes sense, and it is integer data type as well. So in this case, it's both numeric and integer data type. All right, so let's move on to data types in math. Oftentimes when we're doing math, if we're using even specific or specified like integers, the result of the operation may end up being a different class, right? So if you say divide 5L by 2L, something like that cannot be specified as an integer. So it's important to have an understanding of what R does in those situations whenever you're combining maybe different data types in an operation. So say numeric or an integer data type. So if we're just doing something simple like 2 plus 2, we didn't specify that these were integers. And so of course the answer is 4 and the data type is numeric. However, if we specify integers, the output of 2L plus 2L can be stored as an integer. And so that's what's done in this case. If we do something like the square root of 2, of course, that's going to be a decimal number. And so that will be numeric data type. All right, so now play around with these, do some of these basic operations, an integer plus an integer, integer plus numeric, and see what the data type of the result is. All right, I'm just going to copy the solution and run that code. So we can see, again, with two integers and we're adding, that's going to be an integer. Then 6L plus 8, that's going to be numeric. So we're adding an integer here with numeric data. A numeric data type divided by an integer is numeric, as is an integer divided by an integer, or an integer divided by a numeric. And then, of course, the square root of an integer, even though it can be displayed as an integer, is going to be displayed as numeric. So it's taking in this data type, and it may promote that integer data type to numeric to avoid losing any precision in the result. Even like in the case of the square root of 49, we can show that as an integer data because of that operation, that square root operation, it gets promoted to numeric data type. All right, so we have a question. What are the benefits of R over Jupyter Notebook? All right, so you can run R in a Jupyter Notebook. Are you talking about like Python? The benefits of R over Python. So Python is it's honestly my favorite language. It's a very general language that's used, across a wide variety of disciplines, and it's very powerful too. And a lot of the things that we do in R, especially when we start working with things like matrices and data frames, if you're familiar with Python and libraries like pandas and NumPy, you'll see a lot of similarity there. The great thing about R is it's really good at things like vector and matrix or data frame mathematics. So you can so things that you may code in Python that use like a for loop or a while loop or something like that can be done in like a single line in R. That makes for loops in R. It'd be a lot slower to run the for loop rather than just applying whatever you need to an entire matrix or a vector or something like that. So it can be very fast in that way. And also, if we're looking at something that's discipline specific, like I said, I come from the life sciences background, specifically genomics, and there are a lot of packages that were developed for analyzing that type of data, and there are packages available for every subdiscipline. And so a lot of people get into R to use, like, say, a specific software package or something like that, but they miss all of the fundamentals and the basics of R. The goal of this is really to kind of build that up to where you can get into whatever discipline you're in and start using some of those more discipline-specific packages. Did that answer the question? Okay. All right, so let's move on to conditional operators. So if you are familiar with Python, a lot of these should look similar. We have our less than or equal to, greater than or equal to, so all kind of standard notations. Equal to is going to be two equal symbols, and we'll cover why it's two in the next topic. Not equal to is a exclamation point and then the equal symbol. And then to do like multiple comparisons, we can use the or and statements, which is just for or, it's the pipe, the vertical pipe. And for and it is the ampersand. All right, so if we look at how this works, so we can see 1 greater than 1, and that's going to return a Boolean value of false. And then that's going to, of course, be the logical type data because that's what that returns. If we look at, say, this comparison, true and false, that'll again return this logical value here because it can't be true and false. All right, so that's our class, is logical type. So take a few minutes and complete this independent exercise. There are two sections, checking whether an integer is greater than numeric, integer equal to numeric that has the same mathematical value, and then numeric or logical. And then one that's a little more difficult, to write an expression to check if a number is between two other numbers, and that result should be logical type. All right, this should return true. It's true. And then numeric or logical. So if we do 1.5 or true, let's do actually false. And that returns true. Let's try 0. And that's false. All right, but if we do 1, it's true. So this is a weird one. If we're comparing, we say numeric or logical. In this case, R is interpreting 1 as being true, that binary format that we talked about when we first introduced data types, and 0 as being false. So false or false is going to equal false. And 1 or false will equal true because 1 is true. So true or false, there is one true in there, and so it will equal true. What's kind of weird about R is if we run something like 11 or false, it still comes back true. So R actually interprets any number that's not 0 as true, which is just a weird kind of quirk in R. All right, so yeah, that's one way to do it. 2 is greater than 1 and 2 is less than 4. Anybody come up with something different? Oh, perfect. All right. I'm not sure why the 2 ampersand symbols work there. I'm gonna have to check that out. All right, great. So we got true again. All right, so good job. All right, so we can also convert data types using the as dot function, or as dot type functions. So very similar to the is dot type functions, but in this case, we are actually converting. So here we're going to convert the character data true to logical type, the character data 0.5 to numeric type, 1.0 to an integer, and false to a character. All right, so we can see now it's true, no quotations, 0.5, no quotations. We have just 1, and false now in quotations, meaning that it's character data type. All right, so we can also just throw this as.logical inside of the class function to check and make sure that it worked properly. So we do class is true. Yeah, let's do this. So it's data type, and then there we go. It's first data character type, and then after we convert it, it's logical. So again, kind of chaining these functions together to check and see that the as.logical function worked. All right, so this is the last independent exercise. Let's just go ahead and do this together. We want to convert 4.7 to an integer. All right, so if I run this, all right, it comes back 4. All right, so that's one thing that we wanted to point out, is that if you're converting 4.7, it's just going to lop off that decimal point. It's not going to say like round it up, right? So it's not necessarily the best function for doing something like that. there is a function, and appropriately it is named round. All right, so now we're going to do up to a numeric type of data. All right, so trying to convert up into numeric failed. And so we introduced the NA by coercion. So it's still, this is an important aspect of R as well. It still did the operation. It just produced a warning. And so oftentimes, we'll see this later on in, I think, vectors, is that even if you're doing something and it may not be what you're trying to do, if R can do it, it will do it and produce a warning. So you'll get a result oftentimes, but it may not be the result that you expect. All right, so we have a question in chat. I got the error message, failed to load Cairo DLL. I'm not sure what that error message means. Since you're not on our system, someone else may know from our staff, but since you're working on a different system, I don't know that we can necessarily troubleshoot.
Is this about a DLL
Yeah,
message?
the chat.
That sounds more like a Windows thing. Eh? Are you running?
She's Shashi's running on the SDSC cluster.
I'm not sure. I'm not familiar with this message. Like when I see DLL, I think, okay, that's Windows, but I might be wrong.
All right. Next, we'll convert one to a logical type data. Let's see if this works. All right, true. All right. Well, now let's test my theory earlier. 0 is false. All right. 1, 2, 3, 4 is true. What about a negative number? Now I don't know what's going to happen. It's true. All right. So again, any number besides 0, R is going to interpret as true. All right. Welcome back, everybody. Can everybody see my notebook here? Thumbs up.
I can at least. Yeah.
Okay, thanks, Marinas. All right, there we go. All right, so let's move on to the next topic. We're going to be talking now about how to create variables. And to do that in R, there are two different things we can use. So either the less than and a dash, as shown here, with the variable name on the left and the value that you want to assign to it on the right, or the equal sign. And they both work the same. It's really a matter of choice as to what you think looks best or what you want to use. So if we run this, it ran successfully, but we get no output. And that's just because we've only assigned the values ABC to text and the number 1 to I, and didn't ask for any output. In order to inspect variables, we can use the print function. So print just sends text to the output. We didn't use this when R was a calculator, but we can use it to do things like print hello world to screen. All right, so you know the typical first program there. Or if we want to assign, say, the number 8 to the variable planets, and then print planets. There we go. I don't know why it showed out there. Now we can see after printing planets, it printed the value that was assigned to it, 8. In R, you can also just call the variable directly, and it'll print the value. It is best practice though to use print to be more explicit in what you're trying to do. But if you're just, on the console or something like that, shorthand and want to see the contents of a variable, you can just type in the variable and it will print it to screen. Just like we did previously with data types, we can use the structure or class functions to check a variable. So if we do run code here, we can see that planets is numeric type. If we use the structure, we can see that it's numeric and then it also prints the value itself. So this illustrates why structure may be used over class, because it's showing you both the data type and the contents of that variable. Whenever we're using structure, like on a value that wasn't stored as a variable, it was very obvious what we were asking for, so it didn't make sense, why we'd use structure to view both the contents and the data type. But if we're looking at variables, structure can be handy. All right, so just another example. And here, the not planets variable is character and Pluto are the contents. All right, so here's an exercise. It says, there's a bug in my code. Can you fix it? So if we run code here, oh, that's not what we wanted to happen. What's wrong with this? It's printing out Gus. All right, yes. So in the chat, somebody said, gave this command. All right, so again, yeah, now it's looking for a variable named Gus, since there aren't quotes around it, instead of just printing the character Gus. All right, so we can also use variables in operations in a number of ways. We can store the output from an operation in a variable. So if I run this, nothing's going to happen. Nope. Nothing should happen. A few bugs today. All right, it's going to store X as 3. We can also use previously created variables inside of an operation or an expression. So here, we're assigning the value of 3 to X, and then assigning the output of X times 2 to Y. And we'll just do Y here. See that it's 6. All right, so here we're using this variable in an operation. We can also reassign a variable using its old value in the expression itself. So here we're starting off again, setting X equal to 3. And then here we're going to reassign the outcome of X times 2 to X. That highlighted. All right, let's run code. There we go. All right, so here X has been reassigned the value of the outcome of itself times 2. All right, so there's another independent exercise with a bug. If we run this, object Y not found. All right, so what's the issue here? Right, so Y, we need to assign a value to Y first, because we're calling it in this expression. So we can set Y equal to anything, let's do 3 again, and print Y, and then it's 6. All right. And then the last exercise of this topic before we move on to built-in functions is to create A, which is a variable with a value of 9. We also want to create the variable B and assign it the value of 9 without actually retyping the data value 9. But you can retype the name of variable A. And then finally, we want to print the value of B, which should be 9. All right. So kind of confusing instructions, but all we need to do is A equal to 9, B is equal to A, right? And then print B. All right. So we just used A, the variable, to assign whatever contents it had to the variable B. Now, if we do, let's try this. A equals A plus 2. All right, what's going to happen here? Yeah, I don't know. All right, so it's still 9 because we're changing the value of A after we've already assigned that initial value of A to B. So that may work differently in other languages. I think that works differently in Python, but in R, changing the value of A will not change after you assign it to B, will not change the value of B. Are there any questions on variables before we move on to the next topic? All right, so we've already been using functions throughout this workbook, but let's take a go through this short topic just to cover them a little bit more. So in this first section right here, we can see we're creating A, which is a variable that's going to store the output of this function round. All right, and then this is the basic syntax in R. We take the this first value here is going to be the input argument, and then following that we'll have a comma, and then any additional arguments that we need to provide. And so here we're saying digits is equal to 3, and that's just the number of digits that we want to round to. So if we run this, now we can see that A is equal to 2.979, and we have those 3 digits. Change that to 4. Now it's equal to 2.9787. All right, so this is the basic syntax of using these built-in functions in R. Call the function, and then inside those parentheses, you'll have your input argument, and then comma separated additional arguments following that. To get help with functions, if you're in the console, there's a few quick ways to do this. We can just do question mark followed by the name of the function that you want to look up. And a single question mark is going to search through all the packages that you have loaded. All right, so if we go back and look at RStudio, and I'm going to click on packages. All right, so I have all of these packages installed. All right, but they're not all loaded. All right, so the ones with the check marks are the ones that we have loaded. And in our code, we did that here with the library function. So we loaded learn R, ggplot2, XDS, tidyverse, and readxl. And so you can see that I've got a lot more packages than that, but only a few are loaded. So here's data sets. That's one of the base packages. Let's see. Graphics, again, base packages. So the single question mark is just going to look through the packages that you have loaded. All right, and it'll pull up essentially the usage and description of the function. So head here, and then we'll have the input value, and then this is showing some of the different ways to use it. So we can say this is the number of It's going to be the number of lines. And the arguments down here. So n is an integer vector of length up to dimension x. And so essentially this is selecting the using head, which will look at the very beginning of a file, and then how many lines that you want to look at. So it returns the first or last parts of a vector, matrix, table, data frame, or function. And then you can specify how many lines you want to look at. If we want to search all the packages that we have installed and not just the ones that we have loaded, we can use 2 question marks before the function we want help with. But if we run this, you can see I had a lot of packages. And so this help isn't going to be as useful in this case. But if there's a function that you know of that you can't remember maybe what package it's in or something like that, the 2 question marks could be helpful in searching for it. All right, so we need to learn or use the information we learned in head to look at the first 10 lines of something called iris. All right, so we'll start off by saying head iris, which is a built-in data set. And then here it's popping up already. We can say n equals 10. All right, so this is actually a data frame or a table with showing that the first 10 rows. It has a bunch of measurements from different species of irises. All right, any questions on that before we move on to data structures?
One question, Wes.
Mm-hmm.
So when we're looking for for example, the question mark head, is it from all the things that are already installed in my R, or is it like throughout all the libraries across our system?
That's a good question. So the single question mark is going to look at stuff that's loaded, and so that's already installed on your system. The double question mark is packages that you have installed. Okay. So it will be, yeah, all of those that you have installed on your system or your laptop or something.
Okay, so for example, if I don't have, let's say, ggplot in my laptop, it won't appear if I put a question mark there. Okay.
Right. Yeah, great question. All right, so let's move on to vectors. And so as we talked about with data types, let me back up. Vectors in R are one of the most fundamental data structures. It's a data object that's kind of similar to a list, but it contains only matching element types or data types. So you can't have a vector with Boolean and numeric data in it. It has to be either all logical data or all numeric data, or the like. So, and like we talked about with data types, we'll be looking at 4 different vector types. So we have logical, excuse me. We have logical, integer, numeric, and character vector types. To create vectors in R, there's a number of different methods. We'll start off with just the colon operator. And let's see how this works. So we're using the colon operator, and then we're saying 1:6, assigning that to V1, and we're going to print and look at the class. So this creates a vector from 1 with numbers 1 to 6 as integers. All right, so that's a really short way to create a vector of just a list of integer numbers going from the range that you specify. We can also use the seek function, which allows us a little more control over how we're going to what the vector that we're going to create. So we start off here, we're creating this v2 variable, and we're going to assign it the output of the seek function. And the first number is where we start, the starting number. The second number that we give it is the ending value. And then we have this last argument, which is the increment. So by equals 1. So that's how much we increase each time we're working our way through these two numbers. So if we run this code, we should get a vector of, there we go, of numbers that increase by 1 up to and including, if possible, that highest number, so 10.5. And this is the numeric data type. All right, so there's an independent exercise. You need to create a vector of numeric class with numbers ranging from 12 to 19 with an increment of 0.3. And we'll call that, or assign it to the variable v3 and print it to screen afterwards. And we'll also use the class function to determine if it is numeric. So I'll give you a minute to do that, and then we can look at it together. All right, so we'll start off with v3, and we'll say that's equal to seek, and we want to go from 12 to 19. These are comma separated. By equals 0.3. And then let's print v3 and do class v3. All right, so in this case, now we've got this much longer vector going from 12 up to 18.9. So the point of this is that it goes up to the point that it can keep increasing without passing that ending number. So here we're ending our vector with 18.9. And again, it's numeric. All right, let's move on to creating vectors using the C, the combine function, also sometimes called the concatenate function. And to use this, all we need to do is essentially call the function, and then inside of the parentheses, provide the elements of the vector that we want. All right, so here we're creating a vector that we're naming num vector, and it's going to have 1, 5, 3, and 2 in it. And then down here, we have a vector of character data. And again, we're using that C, that combine or concatenate function, to combine all of the elements inside the parentheses into a single vector. I had that highlighted when I ran. That caused the issue. There we go. All right, so we've put in our vector, our num vector, it's numeric, and then our character vector, and it's characters. So C is a really powerful one as well. It's probably the most commonly used one, or commonly used function to create vectors in R, because it allows us to fully control the input of the elements going into that vector. All right, so let's take a deeper look at that combine function. The first thing we're going to do is create a vector named mixed vector with the C function including the elements true, 12, hello, and 1. So mixed vector equals C, and in the parentheses we're putting true, 12, hello, and 1. Then let's print this. And then let's look at the class. Does anybody have a guess as to what's going to happen here? Can we have a vector with different element types in it? Or different data types? All right, do we think this is going to throw an error or do something else? It's just a wild guess now, so. Something else. All right, that's a good guess. All right, so you can see in order to create this vector, R had to, I don't want to say promote, it had to modify all the elements of the vector into a single data type. And the easiest one, or the best one to do that with, the best data type to do that with, would be character data. And so it converted all of those elements to character data types by just throwing quotes around them. All right, if we do a numbers vector with different types of numbers, 12, 2L, again, that really weird way to specify integers, 45.5, print numbers, and class numbers, and run code. All right, you can see that again, here it promoted or changed that 2L to numeric data type in order to be able to create the vector with a single data type. All right, so as I mentioned earlier with that great question about the utility of R, one of the great things that you can do is mathematical operations with vectors and matrices and data frames and such. So let's take a look at that. We're first going to create our two vectors here, one named V1, which is 1 to 4 with an increment of 0.5. And then the second vector, we're just using the colon operator, going from 1 to 7. We're going to examine both of these vectors. And then finally, we're going to add them together and print it. Highlighted, there we go. All right, so we can see we've created our first two vectors. And then what's happened here is that we've gone element by element and added those two vectors. So 1 plus 1 is 2, 1.5 plus 2 is 3.5, 2.0 plus 3 is 5, and so on. So it's just doing it element by element, going down the list of the length of both of those vectors. Now we have an independent exercise, which I'll just go ahead and do alongside you. We're going to first create and print a vector labeled V4 using the seek operator with numbers ranging from 5 to 12 with an increment of 1. So V4 equals seek 5, 12, phi equals 1. Next, create and print we have to print V4. All right, next
should it be equal or should it be the arrow thingy?
It can be either. That's a weird quirk about R, is that you can use either one to assign values to a variable. I just like to use equal that I write in Python sometimes too, and so it's one less keystroke, but either way is fine. In fact, let's just do that. V5 is going to be equal to 2 to 5 with a colon operator. And then we'll print it. And then it wants us to multiply the two vectors together and save the result into V6 and then print it. So V6 equals V4 asterisk or multiplication operator times V5 and then print V6. All right, so little typo there. In case you're wondering, R is not this slow. That's just a function of using this workbook. Sometimes this workbook can be slow. R is not incredibly slow at doing basic tasks. So we've got our two vectors, 5 to 12, and then 2 to 5. All right, and so now we have vectors of two different lengths, right? So what happens here is that R is going to say 5 times 2, that's equal to 10, 6 times 13 is equal to 18, 7 times 4 is 28, 8 times 5 is 40. All right, and so we've reached the end of this vector, but R just starts over. So 9 times 2 is equal to 18. All right, so it's going to loop over that shorter vector again until it reaches the end of the longer one. So if we take this code now and just copy it and paste it in here, and we change the range from 5 to 13, all right, what's going to happen here? So like I mentioned earlier, R is going to complete this task and it's going to give you output. But now the vectors, the shorter vector isn't a multiple of the longer one. So it doesn't, it's not a, let's say, a clean operation, right? So it's going to work through this longer vector and give you the same results, 10, 18, 28, 40, and then it's going to start over again, 18, now 30 times 10, 4 times 11, 12 times 5, but then it starts over again, and it produces the vector that you asked for, but it does so with a warning because it didn't make it to the end of the shorter vector a third time. It only made it partially way through the end of that vector. So this is important to note if you're writing like long bits of code in R, is to keep an eye out for warning messages because you may be able to run the code successfully, but it may not be producing the results that you're intending to produce. All right, so we can use the names function to actually assign names to our vectors. So this can be handy if we want to say like assign meaning to like a random vector of numbers or something to make it more human friendly. And to do that, the syntax is a little bit different than what we've seen. We first create our vector here. So this is student populations, and it's just a vector of numeric data. And then to apply names to those elements, we'll use that names function, and then on the variable. But then we have to assign another vector, a vector of names, to that. And so here I've provided just a list of 4 different universities. So when we run this, now we have a vector, right, with our, and it has all the same data types. But we've given it more meaning, I think, with now, Texas A&M has 72,000 students, University of Alabama, University of Georgia, and so on. So it allows that where we, it's more human friendly, and it'll also allow us to later select elements from a vector, which is what we'll start covering next. Are there any questions about the names function? It's a little odd, and it takes some practice to get used to, but
so in this case, the vector for name should match exactly to so if there are like 4 for student population, it should be 4 for names, is it?
correct. Let's try that though. That's a good question. So let's just remove this and see what happens. I'm not sure. We make it okay. So here now we've got NA. Yeah, great question. Awesome. We always encourage people to break things when they're trying to learn coding. Write code that you don't know what's going to happen, and that helps you figure out what's going on under the hood more often. All right. So one way to select elements or of a vector or subset of vector is to use square brackets to print which elements you want to see. In this case, the index of the element. And so R is different in Python in that it's a one-based index. So is anybody familiar with Python? Right. So what is in Python is different in that like what would Sunday be if we wanted to index this? It would be the 0 element, right? So in R it's 1. All right. So in the square brackets we'll do 1. And so now we can see that we printed just Sunday and selected a single element from the days of the week vector using the square brackets. We can also select multiple elements at once. So like we did with vectors earlier, you can create a vector of different elements to select and just place that in between the square brackets. So if we do days of the week and we wanted to print just the first 3 using the square bracket method, we do days of the week. And then in our brackets, we provide a vector. And so here we'll create a vector using C, and we'll say 1, 2, 3. All right, so here we've combining these functions. Here the combine function to create the vector inside of the square brackets that we're using to select elements of days of the week, and then printing that to screen. We can also use the colon operator. So here we don't need that C function. We'll just do 4 to 7. And that should give us Wednesday through Saturday. All right. We can also use a similar method to remove elements from a list. So to do this, we'll just put a dash or negative in front of the element that we want to remove. So to remove all of the weekdays from days of the week, we provide a vector of -2, -3, -4, -5, and -6. And that should allow us to retain only the 1st and 7th elements of the vector. And I highlighted, and again, there we go. All right. So that's how we can remove elements of a vector, and then here we assigned it to a new variable. Like I mentioned earlier, we can also just use the names that we've created for a vector to select a certain element, which makes it, again, I think if you're going to do something like interact with a database or something, it makes it a lot more user-friendly. Instead of, if we have a vector of 40 different student populations, it'd be easier to search up Texas A&M or University of Alabama or Binghamton or whatever it is, rather than count down which place that is in the vector. Maybe the 25th one, so we'd have to count the elements to select just the 25th one. Whereas if it has a name, we can just look for the name and print that, and then it'll print out both the name and that element of the vector. All right, so I'm going to give you a few minutes to work on this independent exercise. What you want to do is finish the code to combine the last two elements of annuals, so germanium and snapdragon, with the first three elements of perennials, so oxeye, daisy, rosemary, and verbena, into a new vector named mygarden. Use both the C function and the colon operator, and then print to the new vector, and then print the new vector, excuse me. All right, so I'll give you a few minutes to do that. If you finish it and want to share your code in the chat, I would really welcome that, and I can just copy and paste it, and we can see how everyone managed to do this. So a couple minutes to do this exercise. All right, Ian shared some good looking code here. My garden, and then created a new vector with C, and then did annuals 4 to 5 and perennials 1 to 3. I think this is a little bit different than the solution that's written into the notebook. My goodness, that's a new feature, is the highlighting and not running the full code block. There we go. So we have germanium, snapdragon, oxeye, daisy, rosemary, and verbena. That's nice. I really like that. That's clean. Here's the solution. All right, and in this case, we've replaced one of the initial subsetting with the C method here. It's a little, I don't think it doesn't look as clean as Ian's. I like Ian's better, but the same results. All right. So this next exercise, we're going to create a vector named new study group by removing Pierce from study group, and then print the new vector. Interesting. I don't know. Let's see if the minus will work on character data. I don't know. All right, invalid argument to unary operator. All right, so it does not work with character data like this. All right, so in this case, we would have to count 1, 2, 3, 4, 5, and run this. And now we've got a new vector that doesn't include Pierce. In this solution, however, there is a another method. So if we look at this, we're saying we want we'll call it, I guess it's fine, we'll say study group again. But when we're selecting, we're going to look at this vector and say things that are not equal to Pierce. All right, do we remember that comparative operator there, the not equal. And if we run study group, oh, I have that highlighted. That's going to throw an error. All right, and so again, we've got our study group now without Pierce in it. All right, one more exercise. This is just to use practice using the names to print out the value in levels. So if we do print levels, and then here, let's just try emerald. All right. So again, this names function allows us to easily select, in this case, the altitude at which we would most likely find emeralds in Minecraft. All right. Any questions on selecting elements of a vector so far? Kind of thumbs up if we're ready to move on. Why can't you use names instead of levels? I don't understand the question. So you like this right here?
Yes, exactly. Instead of names, it will be levels.
Yeah, it'd be levels. Names is the function that assigns those values, those names to the levels. So here, yeah, you'd be called, it's essentially referring to a function rather than the actual vector itself.
Okay, I thought names was the variable name.
No, and this is a really weird one. That's why I mentioned earlier that the syntax of this is a little, and the structure is a little odd, because it takes some getting used to with this practice right here. Yeah, no, it still it throws me sometimes too. I totally understand.
Perfect, thank you.
Yeah, no problem. Thank you. Great question. All right. So next, let's move on to using our conditional operators to select elements of a vector. We've already seen these. They're just there for reference. If we apply these, though, to a vector, so in this case, we're creating a vector 1, 3, 11, 4, 16, and 17, and we're looking for elements that are greater than or equal to 10. What it returns is actually a vector of Boolean values or logical values in which it's making that comparison for each element of the vector. It's not returning the elements of the vector that are true in that evaluation. Rather, it's returning the full length vector with those logical values. But we can take that vector and use it to select elements from the initial vector. So in this example, we have a vector of, say, car prices. And then we're going to create this new vector of Boolean values called affordable cars. And that is going to be this comparison of car prices that are less than or equal to 25,000. So if I add in here, print affordable cars, and then down here, I'm going to use that vector of logical values that we created to only select elements for which it's true. All right, so here, now we printed off affordable cars. It's true, false, 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 true. And then when we selected from car prices using that new vector of Boolean values, it pulled the first one, right, where it was true, and the last one. If we want to get even, if we want to use two operators, we can do use the or, that vertical pipe, or the and that'll create a vector of values based on that comparison. So if we do print highs and lows, all right, so here we've selected everything that's either below 25,000 or more than 60,000. All right. If you would like additional exercises, today's workbook is based on a larger volume of material that we have. So if you want like additional exercises and things for certain topics, you can just let me know and I can get that to you. We have additional portions of the workbook that we can share. This was just scheduled to get done within essentially a 5-hour period, whereas oftentimes we'll cover this much material over 2 days or something. So you're really getting a kind of a high-speed run through R. All right, are we good to move on to the next topic? All right, so the next topic is another data structure. This is matrices. And so they're very similar to vectors in that you can only have a single data type. So either numeric, character, or logical, or like integer, right? But they are the two-dimensional arrays. So to create these, we use a function called matrix, right? Appropriately enough. And then we provide it with a vector of for input. And then we can specify in this argument whether to do it by row. And then we specify here the number of rows. So if we print this, oh no, I did it again. All right, so we asked for by row equals true. So as we're going through this vector, it's going to fill out the rows first. And we asked for 6 rows. So 1, 2, 3, 4, 5, 6, and so on. All right, so we can change this to say false and in row to 4. And if we do this, then it will fill the columns first. And now we have 4 rows and 3 columns. All right, so we have an independent exercise with 2 parts. Go ahead and complete this exercise. And once you have it done, if you want to share it in the chat, that'd be great. I'll give you a couple minutes to do this first part and the second part. All right, so we'll start off with my matrix. Oh. And we're going to use the matrix function. And we're going to go 13 to 24. By row equal to false. And in row equal to 4. And then print my matrix. All right, so we have this nice matrix going from 13 to 24. Again, filling out the columns first. And then moving on to the next one after it reaches the number of rows. If we take this code and copy it, but change this to 12 and run, what's going to happen?
Wes, I have a quick question.
Yeah,
So
of
why did
course.
why did we change it to like by row equal to false?
It's just to get familiar with that. There was no reason. It was just to show, how it did it. Filling up the columns first rather than the rows. All right, and so again, we get this warning because the data length is not a submultiple or multiple of the number of rows. So R created this matrix for us still, filling out the columns 12, 13, 14, 15. But when it started to fill up the fourth column with 24, it ran out of numbers in our vector. And so it had to start over. It didn't get to the end of that vector before it ended the matrix. So it had to, or it threw a warning. It still created it, but it threw a warning. All right. So we can use the matrix function on our own data that may be a lot more interesting than generating like a random vector of numbers, right? So in this example here, we've got essentially 4 vectors representing 4 countries, and then in those vectors we have the GDP in trillions, the percent growth, their GDP percent growth, the population, and GDP per capita of each country. So take a few minutes here and try to figure out how to convert these vectors into a new matrix named GDP by country, and then print that new matrix. All right. We've got one in the chat. That looks good. All right. So here we're creating a new vector named all countries, in which we're using that C to combine our previous vectors. All right, so this is great. This is fantastic. It's real clean. We know exactly what we're doing here, and we're creating essentially a vector of vectors, which is was the hint, right? So, and then we can use this matrix function to assign this input value now that we created all countries, and we'll say by row is equal to true, which is correct, so that it fills out in order across each country, and then print GDP by country. Oops. All right, so that's a great solution. We've got 19.485, 2.27. So this first row represents the United States, the second one, China, third, Japan, and then Germany. All right, great. We also could have just done this right here. Let's try this. All right, and we get the same result, right? So here we're creating that vector of vectors inside of the matrix call. There are 2 great ways to do it. The original way, I think, was probably more readable. And so I like that, even though it was an extra line of code, it was easier to interpret and understand what was happening. So awesome job. All right, let's move on to, let's see what time it is. Okay. Adding additional columns and rows. So a lot of the methods that we are going to be using for, oh, my elements in the matrix are showing up in this format. Can you post the code that you're running? So it's the same code. In row. All right, I'm just gonna try this and see if I get the same thing. All right, so the issue here is that we didn't specify by row is equal to true. All right. Yeah, so it's a matrix issue too. So like vectors, we can only have a single data type. We'll go over, we'll move into data frames next, which are far more useful and handy. So weird stuff can happen because it's trying to convert all of those numbers to a single data type whenever you're working with matrices. But a lot of these stuff that we're looking at, we're kind of working our way up to data frames. So a lot of the methods that we're learning inside of matrices, we can apply later with data frames, which is where just R really starts to shine. It's like, if you're familiar with like Python and pandas, I love pandas. It's very similar to R. So you'll really like when you get to data frames, I think. All right. All right, so here we can talk about adding additional columns and rows to a matrix. And the functions to do that are cbind and rbind. So cbind for binding columns together and rbind for binding rows together. And so to do that, we're going to create this new vector called GDP share. So we're just adding in a new stat here. And then we'll use the cbind function to add GDP by country, or to combine GDP by country and GDP underscore share. So if we run this, now we've got this additional column here that we added, this GDP share. So I removed, there was additional information in these exercises about adding column names and row names to a matrix. It's very similar to what we did with vectors. And so here it's automatically naming this column, but we haven't supplied names for this yet, which we could do. And if you want that information, I'd be happy to send it to you. But it's very similar to how we did it with vectors. All right, so in this independent exercise, we are going to use the rbind function now to add this information to our GDP by country matrix. All right, so I'll give you a minute or two to look at this and then we can go through it. Oh no, I lost my code. All right, I'll cheat. All right, so for this one, again, all we have to do is create this new vector that we named Brazil, and then use that rbind function to combine our GDP by country and the new vector we created, and then print it to screen. All right, are there any questions on what we've covered so far today? All right, if there are no questions, I think that we can break for lunch. And so we'll start back at 1:30. I'll stick around for 5 minutes in case there are any questions, but then I need to go grab something to eat. But then I'll be around for most of the lunch break if you want to post something in the meeting chat or if you have any other questions, then please let me know. All right, so can everybody see my workbook now, subsetting parts of a matrix? All right, can I get a thumbs up in the chat or? All right, thank you, Google. All right, Brian, thank you. And all right, all right. So welcome back. Let's pick up with subsetting parts of a matrix. So we did this with vectors in an earlier topic, and it's very similar. We're still using these square brackets, but now we have to specify rows and columns, right? Instead of just the index number of the vector. So to do that, we would just type in the name of the matrix here. And the first number corresponds to the row, and then we separate it with a comma, and then give it the name of the number of the column that we want to choose. To select a group within the matrix, we can provide a vector like this for rows 1 and 2, and that comma, and then rows 5 and 6. So if we look at this independent exercise, we'll go ahead and do this together. The first thing we're going to do is create a new matrix called my matrix. And it will be 24 elements. So we'll do matrix 1, 24. And we'll do let's do by row equals true, and in row we'll set that to 4, what it asks. All right. Next, we want to select the matrix element that is in row 2, column 3, and assign it to the variable named subset 1. So subset 1 will be my matrix, and we'll just provide the row and column in those square brackets. And then we are going to make another subset called subset 2, and we'll do my matrix. And then that will be rows 3 and 4, and columns 1 through 2. And then we'll go ahead and print all of them. All right, so the element in the second row and third column should be 9 in subset 1. And that's what we got. So that's good. And the third and fourth columns, rows 1 and, rows 3 and 4 in columns 1 and 2 will be 13 and 14 and 19 and 20. All right, great. Let's look at something else. Let's try this. We'll do. All right, so here we've just specified a row that we want, and we left the column blank. So that's going to print out all of the elements of that row of the matrix. So here we're doing the second row, and that is 7 through 12. On this next example, we have the comma first, so we didn't specify which rows to print. And we're just grabbing columns 1 and 2, and it's going to print the full length of that column. All right, so 1 through 19 and 2 through 20. All right, we'll use that a little bit more with data frames as well. Are there any questions on subsetting a matrix with the square brackets? All right. Let's move on to math with matrices then. So here again, we've got our review of our arithmetic operators. Let's create a new matrix and conduct some simple calculations on it. All right, I'll give you a minute or two to do that. And then if you want to share your code, we can look at and see how R works with math with matrices. All right, let's just let's copy this and we'll just mess around with it for a little bit. All right, so here we're creating a matrix with 12 elements. Oops. All right, and it's going by row. And then when we do our matrix for math, which is what we called it, plus 2, it's just going to add 2 to each element within that matrix. All right, so if we do, modulo, then it's going to return the remainder for each element divided by 2. We can do things like square each number. So again, really powerful for these kind of matrix calculations and things like that you want to do across all elements. And you can even have, far more complicated equations than that. But R is really, really good at doing that type of matrix manipulation and calculation. All right, so we looked at earlier, I think in the first section, R is a calculator, the sum function. And so we can use that on matrices as well. All right, so it gives us the sum of this, essentially this matrix here. Let's print that. Right, which is just essentially numbers 1 through 9. But we also have other built-in functions like row sums, which will provide, as the name suggests, the sum for each row within a matrix. So here, 1 plus 2 plus 3 is 6, 4 plus 5 plus 6 is 15, 7 plus 8 plus 9 is 24. And then we also have call sums or column sums. So just some handy built-in functions for working with matrices and data frames. All right, the last thing I want to cover as far as just basic matrix math is matrix algebra or multiplication. So there's 2 different versions of matrix multiplication in R. There's just a standard kind of multiplication wherein we're just multiplying, the element in matrix 1 that corresponds to the element in matrix 2 to produce the corresponding value in the final matrix, right? So 1 times 7 is 7, 2 times 8 is 16, 3 times 9 is 27, and so on. All right, but this isn't, may not be the type of matrix multiplication that you're interested in doing, which would be the algebraic matrix multiplication. But that is there is a function for that in R that's built in, where we surround our multiplication operator, that asterisk, with percentage symbols on each side. And so for this, to do this kind of matrix multiplication, I think it's the number of columns in one matrix has to equal the number of rows in the next. I haven't really done this extensively since like the 8th grade. So I don't have a need for matrix multiplication in this way, but if you do, we do have that capability. Right, so we have 2 rows in the first column, 2 columns and 3 rows in the next matrix, excuse me, and then we end up with this, the result of that algebraic matrix multiplication. So I'm not sure if you'll use that. I just wanted everybody to be aware that that functionality exists within R. All right. All right. Any questions on matrices before we move on to data frames? Or if you're ready, can you put a thumb up in the chat or? All right, it looks like we don't have any questions. We're getting some thumbs up. We're good to go. So we're going to move on to data frames, which I think is where stuff starts to get really interesting with R and gets really useful. So data frames are essentially like tables or two-dimensional arrays. They differ from matrices in that you can store all sorts of different types of data. So it is probably one of the most fundamental and commonly used data structures in R. Because if we just think of like Excel spreadsheets or something like that, that type of data is perfect for a data frame. There are some rules. The columns need to be named, right? But you are allowed duplicate names for the columns. The columns need to be of equal lengths. And the row names need to be there and they need to be unique. That's kind of the identifier that we use to separate everything out. So there are some built-in data frames in R. If we want to take a look at one, we can just type in the name. Empty cars is one that's built in. So if we run code, we can see this nice data frame, which is displayed here, just as a table with the row names, which would be the make and model of these different cars, and then some different stats for each of them. So like the miles per gallon, the number of cylinders in the engine, the displacement, which is the size of the engine, the horsepower, and so on. There's a lot of different values there. So the top of this output is called the header. So we can see here where we've got these column names, and then each row is a data row. And then within each of those, we have a cell. We can look at more of this or less of this using those head and tail commands that we looked at earlier. So here we're only going to look at the first 6 rows, or here we're going to look at the last 6 rows. So another way to examine your data frames that we talked about earlier with the built-in functions. We can also use that structure function that we did earlier. So we'll run this code here. And this provides kind of a deeper insight into the data frame itself. We have 32 observations. So that's going to be the 32 unique row names of 11 variables. And so those are going to be our column names. And like I went over, miles per gallon is one of those variables, number of cylinders, displacement, horsepower, and so on. I don't know what all of these mean. All right. Any questions so far on data frames? It's I think that I don't want to say the most interesting data structure. It's the one that's really commonly used and where we start to get into kind of where R really starts to shine. All right. So similar to matrices, we can create data frames in R using the function data.frame. So let's take a look at this code chunk to see how we set this up. Essentially, we've got these different vectors here that we're creating. The first one is players. These going to be player names. And this is for baseball. Then we have a vector of the positions. So this is going to be the different positions that these players each play. So designated hitter, first base, shortstop, and so on. The team that these individuals play on, and then the specific league that their team is in. So we have the AL League and the NL League. And then some stats, so their batting average, their RBIs, and their home runs, which are all kind of frequently looked at baseball stats. So to create this data frame, now that we have all these vectors that we want, we'll use this data.frame function, and we're going to assign the output of that to what we're calling MLB stats. And then here's where things are a little tricky. So we start to define what makes up our data frame with our columns. We can say position, all right, is going to equal the position vector. The next column in our data frame will be team, and it's going to equal the team vector. League will equal the league vector, and so on. And then the one thing that we do need to specify differently would be the row names, which need to be unique. And that would be our players. All right. So if we run this code, now we've created this nice data frame displayed as a table here with our unique row names over here as the player's name, the position they play, which is character data, the team they play on, character data, the league, character, and then all this numeric data, the average, the RBIs, and the home runs. All right. So the next exercise is for you to create your own data frame using this table here. So I'll give you a few minutes to go through and create your own data frame. You can go back and look at this code up here and rework it to fit in with this data, and then create this Aggies data frame. So I'll give you a few minutes to do that. All right. And so a lot of times we're obviously not going to be typing stuff like that in. We'll be, importing a table that we have, or from Excel or a CSV file, and then converting that into a data frame, or working with the output from some other program that's already been issued in a data frame. But I think it's important to get the fundamentals down of how to create these. So word, all right, Aggies is going to equal data dot frame, and then we'll say year equals year, major equals major, days are equals days are, and then finally row dot names equals students. All right, and then print Aggies. All right, great. So we've got this nice table again, Kyle F. Field, Rudder T. Complex, all of our student names we put in, the year that they are currently in university, their major, and the days they've been learning are. All right, are there any questions on how to create data frames? All right, are we good to move on to subsetting? All right. Thank you. Let's go ahead and thank you, everybody. All right, so this should be something you already know how to do, right? We looked at this with matrices. So go ahead and take a minute and see if you can figure out how to complete this independent exercise below. And know that the MLB stats data frame is already loaded in here. So if we do this, we can. All right, to select the second column from row 4, remember with our square brackets, the first number is the row number, and the second one is the column number. So we specified row 4, column 2, and then next we want to do offense, which is equal to, again, MLB stats, and then select columns 4 through 6, rows 1 and 2. So rows 1 through 2 and 4 through 6. And then we'll do print offense. All right, so we went in and grabbed a subset of this data, right? It saved our column names or printed those out as well as our row names. So that's a really nice view and something a little bit different than the matrices. So that's how we'd use those square brackets to subset a data frame. And if you're working with a small data frame or something that comes out like in a kind of a standard format where you know exactly what rows and columns you want, that can be really useful. But if you have a very large data frame and you want to look up a specific bit of information, then it would it'd be beneficial if we could do it in a more human-friendly way, right? So we can also use our row names and our column names within the square brackets to go in and subset data or look up something in our data frame. So in this example right here, I am interested in Shohei Ohtani's batting average, right? So I selected the row name first, and then the specific value or the column variable or observation that I wanted to look at. In this second example here, I'm not selecting the row name, but the only thing I'm interested in is that RBI number. So if I run this, I can see that this player's batting average is 0.257. And then this right here is actually just the row or the column of RBIs. All right, so in this independent exercise, we're going to do this together. Again, we're using this MLB stats data frame, and we're going to use row and column names this time to subset the data frame, selecting the team for the player Freddie Freeman. All right, so we'll do, we'll save it as Atlanta equals MLB stats. And then we'll do Freddie Freeman, because that will be our row name. And team, which would be the column. And then print Atlanta. We run this code. It should print out Braves if we did this correctly, because that is the MLB team in Atlanta. And that's what we've selected. All right, there we go. So we selected the correct element, picking up Freddie Freeman's team. Another useful thing, this is something that I actually use really frequently in R, is selecting columns from a data frame using the $sign. And so the structure of this is just calling the data frame and then providing a $sign. And once you do that, R will automatically start to populate a list of options for you to choose from. And in this case, we've already selected RBI, and it will just print out, again, those RBI. So it's a lot easier than having to go in and do the square brackets if we want that entire column. And this is something I use as a shortcut very frequently when I'm using R. So let's do that together. Let's look at teams. So we'll look at MLB stats. Teams. Oops. It's team, not teams. All right, now let's try something. Let's try. let's just print MLB stats. Sometimes the interface for the workbook is a little bit different than what would be normal for the console in like RStudio. So it's not pulling up the column names correctly.
Wes, I have a question.
Mm-hmm.
So we did the $sign RBI for the column previously.
Right.
Is it possible to see the row? For example, if you want to see a player's stats, is it possible to pull it that way?
Not with the $sign. You would still have to do the square brackets.
Okay, like
as far as I know.
previously we
So
did.
yeah, so like that.
Got it. Thank you.
But what's important here is, let's do this. So here we have undefined column selected. So you have to remember, it's a little, the syntax is a little odd. You have to put in that you have to put in the comma there. And then it'll pull up all of the information. So it looks a little weird, right? So you just have to remember that if you get that error, it's because you're missing the comma, because you're dealing with a two-dimensional table, and it doesn't know, you know, what it's supposed to be grabbing from.
Right.
All right. All right. Let's look at this next functionality of data frames, which I really like, is the subset function, which allows you to use those conditional operators to select the subset of the data. And the syntax for this is a little weird as far as the way it looks, because we have to specify what the subset equals, and then do the conditional operator in comparison on the right side of that. So here we're calling the subset function, and then our input argument, which is that data frame that we have, and then we're saying this is the subset that we want to use is the home runs, and we want those to be greater than 40. So if we just copy this and run it. All right, and so now you can see this, we've got this data frame where all of the players here have more than 40 home runs. All right, in this exercise though, it's asking us, we'll just erase this to make it easier, is to create a new data frame. We'll name it AL, or American, I guess, equals subset ML stats. And here the subset would equal the league. And then that has to equal AL. And so that's where it starts to look, to me, the syntax starts to look a little weird whenever we're looking for things that match. All right, and if we run this, we should have a new data frame that includes only players that are in the American League or the AL League. All right, and there we go. All right, so that's the last method I wanted to cover of subsetting data frames. Are there any questions? I know we've raced through a lot, but I'm trying to cover a lot in a short amount of time. Okay, and then you have access to this. You can download it and go back, you know, as frequently as you want. All right, we can also reorder data frames using a new function called the order function. If we run this code, it doesn't automatically order the data frame, right? what it does is it creates kind of a vector of like the row index from each observation and increasing value in R. So if we print off, let's look at this again. We'll print here MLB stats. All right, so we're calling the order function, and then we're doing the order of the HR column, which we're identifying using the data frame $sign method. And so it's saying 3, 8, and 7. So we can see 3 right here is the lowest number in the HR column. And then 8, 7, and then 6, and so on. So it gives us that row index for each value in increasing order. But like we did with our comparative operators earlier with vectors, we can use this to select or to reorder our MLB stats now that we have that vector of row indices. All right, so let's take a look at how we would do this. Let's go ahead and we're going to say average is equal to order. And then we'll do MLB stats. And that is AVG in caps. And so let's go ahead and just work through this. We'll do average. Let's see what we've got so far. All right, so it looks right so far, 6, 7, 1, 5. We go back up and look. 6, 7, 1. All right, so this looks like the correct order. Now we can try to apply this to our MLB stats. And we'll just do average, comma. And all right, so now we've got our data frame reordered going increasing value of the batting average from the lowest 0.249 up to 0.311. All right, bonus points if you can get it in descending order. All right, so there we go. It automatically showed us how to do it. So we'll do decreasing equals true. All right, and now it's in the reverse order, right, with the highest batting average on top. All right, any questions on reordering data frames? All right, we'll move on to factors in data frames. So factors are a kind of a data construct that allows us to sort variables into kind of categorical data. So if you wanted to have, say, categories of slow, medium, and fast, or I don't know, mild, medium, and spicy, stuff like that. We could use factors to organize that data into those different categories, and even to order those rankings or those categories in terms of like speed or I guess spiciness. It was my example. So let's take a look at how factors work in data frames. So what we're going to do here is we're just looking at this MLB stats again. And then we're going to change one of these columns into a factor type by first calling that column that we're interested in, and then assigning the output of using the factor function on the same column, and then we'll print again. All right, so before we changed, we can see, this is the data frame. Then we changed our league to factors, and it did not appear to make a change. However, if we look at the actual structure or the summary, we can see where the change made place. So here we're using the summary function. And now we can look at each column within our data frame. So we have our position and the length of that column, and we can say it's character. Team, same thing, 8 character. League, same thing, 8, and it's character. Now though, whenever we converted it using the factor function, now we can see that there are 2 essentially categories here. We have the AL category and the NL category, and there are 4 in each. So it helps us to summarize and look at our data in a slightly different way. And I wanted to point this out because there are some packages that require certain variables to be stored as factors, just so that you're aware of what that is if you run into it. All right, so we're going to do the same thing. This time we're going to convert position and league to factor, and then we'll do the summary again, just so we have a good handle on it. MLB stats. And then to convert position to a factor, we'll do MLB stats, and then position equals factor MLB stats position, and then MLB stats league is equal to the output from the factor function for MLB stats league, and then summary MLB stats. All right, so we can see now our league is in these nice categories that are even, 4 in the American League, 4 in the National League. But here we have our positions. So we can say we have 2 people that play first base, 1 that's a third baseman, 2 designated hitters, right fielder, and 2 shortstops. All right, so that's all I have time today to cover for data frames. Are there any questions before we move on? Can I get a thumbs up if we're ready for importing and exporting data? All right, thank you. All right, so like we mentioned when we were creating the data frames from scratch earlier, it is a lot of typing. It's very tedious, especially if there's a lot of rows and a lot of observations. There are a lot of both built-in functions and packages that allow you to read in various file formats. So your most standard and like base package would be something like read.csv, right, which reads in CSV files. But there are packages that allow you to kind of extend that functionality, and you can read in like XLSX files from Excel, which is really handy. And you can read in different sheets, and if you have like a multi-sheet Excel document, you can read those in. So we'll go over a little bit of that. And a little bit of, in order to do this, we need to have a better understanding of kind of navigating the file system from within the R console. So if we remember within RStudio, if you are familiar with, Linux terminal, you can do things like ls to list the contents of your directory, ls, 2 dots to get the parental directory's contents, and things like that. But if we're working within the console, there are several R specific commands that we can use. The first is get wd, which just prints your current directory, your working directory. And so if you run this, you should see the path to home, and then your user ID, and then the name of the directory that we're in, which would be ACES _ fundamentals of R programming. All right, so that's how we know where we are. It's also useful if you need to get your file path or directory path, and you don't want to, type out the whole thing or look it up in the files application in the portal. So the other command I wanted to go over was list.files, which is similar to the ls function in list or in Linux. So that's going to list all the files of my current directory. We can also provide a path here. So if I want to list.files, let's say, we'll give it a relative path, see if this works. So those 2 periods mean the directory above in Linux. All right, so it's going to list all of the contents that I have in the directory, in my home directory. Right, so let's do. That was the Linux command, excuse me, get wd. All right, so this relative path is just showing us the files that are in this location, home/u.wb 109972. All right, so this gives us a couple tools to figure out where we are and maybe where a file that we want to import is located. And then it also allows us to check and make sure that if we've exported something, that it lives there and it's saved correctly. All right. Another command is the setwd command, which allows you to change your current directory from the one that you opened your R project in to a new one. But this is considered by some is kind of poor practice because it changes the R environment and can cause problems if you have like an R script and you're trying to share it between, say, members of a lab or something like that. Whenever we're reading in data, it's best to use explicit paths. And to do that, we have to like set up variables where we're saying we're define the path and then use a few more functions in order to load like a CSV file. So to do that, let's look at this pseudo code here. The first thing we do is we set up a variable that's called my data directory, and then we're just going to assign it the path where we want to read our data from. All right, and then to actually read in the data and assign it to my data, we're going to use the read.csv function because our data is going to be in a CSV for this exercise. And then we can concatenate the file path and the file name using the file.path function. And then we call the my data directory variable that we created, and then the name of the CSV file that we want to load. So let's work through how to do this. If we look in our current directory, I'll do list.files again. All right, we can see we've got this king underscore county house underscore data.csv file. And that's the file that I want to read in to into R. So the first thing I want to do is set up a explicit path to the directory. So we can use the git wd command. I'll run this. I can just copy this now. And I can say, we'll call it data directory. We'll just call it data dir equals, and we'll set the path that way. All right, and then to read it in, we'll name it king equals, the first thing we need to do is call our read.csv function. And then we can use the file.path function to piece together the file path, file path, the data directory, so say data dir, and what we want to read in, which was king underscore county. I'm having trouble remembering what it was. Let's just do this. All right, there we go. And I'll copy this. All right, so we have our full file explicitly path explicitly stated by using the file path function inside of the read.csv function. And then we want to look at, we'll do head first, king, and let's see how this works. All right, so now you can see we've got this table that we've imported from a CSV. And if we do str on it, the structure function, we can see it reads it in automatically as a data frame. And so we're good to go. And this table has 21,613 observations in 21 variables. So again, it's not something that you'd want to type out in R to create your own data frame from scratch. We've got this already now stored as a variable. King is our data frame, and so we can start working with it immediately.
Wes, can you again like explain the directory, like how we set up everything?
Yeah. Let me go through it again because it's confusing for sure. Let me just start over, okay, and go through it one more time because it's not the most user friendly method, but it is, I think, a good practice. So let's do the first thing we want to do is make sure or see where we're working. So we'll do the git wd command, and that's going to provide our path here. Right. So this is the folder, and we know that this king underscore county underscore house underscore data .csv folder lives in there. Right. That's where it is. And so let's set up our first variable. We'll call it the data directory. And then we just set it equal to this. So we'll copy this. And then the next thing we need to do is create a variable that we're going to store our data frame in. And so we're calling that king. And the first function we do is read.csv. All right, so now that the CSV needs just a path to the file. And so we're using the file.path function to paste together our data directory and our actual CSV that we want, which we found with the list.files function earlier. All right, and then we can do str king. And I've been signed out again for some reason. Were you able to see that before it shut off quickly? Okay, sorry about that. If you're working on your, if you download this to your personal computer, it should save your progress in the output. For some reason, it's not saving it right now. So let me go ahead and just do this again real quickly this time. All right, so now we're in. All right, so that's how we can import a data frame using best practices in R. All right, are there any questions on that? All right. Nothing in chat, okay. So there are a lot of other functions to read in or to write out Excel or CSV files. We're going to be doing the write.csv. It's like a base function. So first, let's copy this just so we're reading in the King data again, making sure it's available in this code cell. And look at how to do this. All right. So now we want to, we've got the CSV file and we want to write out to a another, let's just say we made some changes to it and we're going to write out to another CSV file. We would just use the write.csv function. And the first argument we provide is the data that we want to write out. And then the file that we want to write out to. And here, let's just do something easy and check it out. We'll do king2.csv. And then we'll set row names equal to false. All right, let's just try this. All right, looks like nothing happened. But if we do, let's just do list.files again. And it looks like it's there, king2.csv. Let's hop over to the portal though. If we go to files and home directory, and here it is. We'll just click on it and view it. All right, so now we can see we've got it saved as a CSV. All right, so we could have made whatever changes we wanted or manipulations we wanted, and then saved it that method. All right, you can save to somewhere else. So here, if I wanted to, I could have saved to let's just say /home u.wb/king.csv2. And if I run this, oh, let me. And then go back to my home folder. It should be in here somewhere. There it is, king2.csv, which was made right now. And you can use the same method that we used earlier with the file.path to have it write out to a different directory if you want it to. And that way you're just providing the name that you want to save it as, and then have all of your data like saved into an output directory or something like that. All right, are there any questions over importing and exporting data? All right, let's go ahead and take a 10-minute break, and we'll come back at 3:45, and we'll move on to plotting in R. All right. All right, let's go ahead and get started. We've got, I guess, one more session. I want to thank everybody so far that's stuck through. I know this is really difficult to do via Zoom, and it's a long, quote unquote, short course. So thank you for participating. I really appreciate it. We're going to move on now to base plotting functions in R. So the base version of R, without any additional packages installed, does have plotting functions, and they're really great for like initially exploring a data set, for doing something quick, like looking at a scatter plot or a histogram. And so I wanted to explore those a little bit, and then to create like really nice looking publication ready graphs and things. You'll likely want to use a different package, such as like ggplot2, which is a really popular one for graphing. So we're going to go over the base plotting functions first, as the packages often use the same kind of syntax and formatting. So let's just start with looking at the help for the plot function, which is built in. So this table is kind of a nice summary of, actually, if you run our question mark plot, remember looking at all of the install or the loaded packages. And so this is a nice just summary of that's easier to read. Essentially, for like a scatter plot, we have our x coordinates, our y coordinates that we want to plot, and then these other arguments that we can supply. So the type of plot, the title, subtitle, and then labels for the x and y axes, and then the aspect ratio. So let's just dive into this to see a little bit more of how this works. The best way to figure this out is to play around with it. We're going to be looking at the empty cars data frame again, like we did earlier. And we'll be using this to do some plotting. And so again, we've got the different makes and models, stats like the miles per gallon, number of cylinders, the engine size, the horsepower. Excuse me. So to plot just a very simple plot, looking at the relationship between horsepower and, say, miles per gallon of these two, we can plot our x and y doing this. Again, we're using that dollar sign to call these specific columns, and then we're providing an argument for main, which is the title of the plot we want to build. So if we run this code, you can see it produces a plot. It's not a pretty plot necessarily, right? It's got these ugly y-axis and x-axis labels. The dots aren't great, but it does show the data, and allows us to see that there is a trend here, that whenever we start increasing the horsepower, we see this decrease in our fuel efficiency. All right, so again, really great tool for exploring our data initially, and you can make some modifications. So we're going to build another plot in this exercise. We'll just do this together. We'll do plot, and then we need our x and y values, and so we're using empty cars, engine size or displacement, and our y-axis will be empty cars MPG, and main will equal engine, say engine size versus miles per gallon. And then we'll do sub equals, I don't know, my first plot in R. Label, X lab, we'll set equal to engine size. Call it displacement. And then Y lab or Y label, we'll set to miles per gallon. And it looks like I did something wrong. I don't have a comma. All right, so it's already starting to look better. We've got our main title, and now we've replaced our y-axis label and x-axis label. And we have this subplot. We can even, there's other things we can do too. So we can say, set the color equal to red. You can go in and set which shape you want these to be. If you want them to be solid color or, you know, open circles like this. We'll get more into that when we're doing ggplot2, when we want to really customize how a plot looks. But as far as cleaning up, you know, quickly a basic plot, it's pretty easy to do with the base package. Another thing I wanted to show you quickly in the base package before we move on to ggplot2 is the pairs function, which I think is pretty cool. The first thing we're setting up here is we're going to do a subset of the empty cars data frame, and we're subsetting this time using the square brackets that we looked at this morning. And then starting off with a comma, right, because it's a two-dimensional structure. And then we want to pull just these columns, right? So we're creating this vector of the different columns that we're interested in pulling. And then that's going to create this data frame that we're interested in running the pairs function on. In the pairs function, let's just run it to see, provides these comparisons across all of these different columns. So here we can see displacement or the engine size versus the number of cylinders. So right, as we increase the number of cylinders, we have 4-cylinder, 6-cylinder, 8-cylinder cars, the size of the engine goes up. Displacement versus miles per gallon, we have this negative correlation with the larger engine size correlating with lower miles per gallon.
Wes, quick question.
Yes.
For that code top plot two plot empty cars, there is like a comma in the beginning. Is it like similar to the vector where we are leaving alone, like the rows and the columns come after the comma?
Yeah, exactly.
Okay.
Yeah, so similar to the matrix or the data frame. Yeah, we're that's what we're subsetting. Is this we're pulling those columns? That's exactly right. Yeah. All right. I think this is a really interesting way to plot things. So now we can see cylinders, miles per gallon, all these different correlations real quickly. I think it's a really nice figure, and you can clean this up. So I want to give you a few minutes to play around with the pairs function and try to change the name of the displayed variables to something that's more user-friendly. So I'll give you a couple minutes to look at that, and then we'll move on to histograms. All right, so in order to replace those names and make them a little nicer. If we looked at our help, we saw that there was a function named labels, or an argument named labels. And we had this clue here, you may want to create a new vector that contains the new label. So I first subsetted the values that I wanted to plot. I just copied that from the original one. I created this new vector named pair labels. That's just a vector of what I wanted to replace the names with. So displacement, cylinders, miles per gallon, and horsepower instead of HP. And then just within pairs, I gave it the argument of what we wanted to plot, and then the labels for those different columns. All right, so are there any questions on the pairs function? All right, so there is another base plotting function I want to get to before we dive into ggplot2, and that is the histogram function. So we just look up the help. We can see that this nice breakdown of how this works. Our main title, the X limit, so the range or the breaks, and so forth. Let's go ahead and, all right. If we want to just do a default number or default histogram, we only need to provide a single value that we're plotting, right? For histograms. And so essentially it's just going to print out histogram of whatever you printed is your title, and frequency is your Y label axis or Y axis label, and then what we plotted is the X axis label. And so it's the information's there. It's an ugly gray histogram, but if you need a histogram for something, we can modify it. So if we look at, let's do this quickly since ggplot is kind of a beast and we want more time with that. Let's just look at this real quick. Here we're going to plot the same thing, but we're going to increase the number of breaks, or the number of columns that we want in our histogram or categories. We're going to change the color of the bars, add in this main title of MPG, and then give the X limit a range of 10 to 35. So if we run this, now we can see that all of these are broken up into kind of 20 different steps within the range of 10 to 35. We've got the MPG. We didn't change the X label. We could do that. But it already looks quite a bit nicer. So you can go in and look at this, in the future. I do want to carve off some more time though for ggplot2. All right, so are there any questions before we move on to that? All right, I think we're good. All right, so this is the last section I wanted to cover for today. I want to preface all of this by saying that ggplot2 is a beast, and you could spend, several days, if not weeks, learning how to use ggplot2 and creating really nice graphics. Obviously, we have just under an hour, so kind of want to just dip our toes into this, and kind of get a feel for working with it. ggplot2 comes with a built-in data frame that we're going to be using called MPG. It's really similar to MT cars in that it is cars, but it's broken down. We've got the manufacturer, the model, and then different years, and then things like city mileage, highway mileage, and things like that. So we'll play around with this to plot. And we're going to start off by going over how ggplot works. So it's different than plot in that it builds the graphs kind of layer by layer. And so you kind of initialize a ggplot object, and then you start adding things to it. And to initialize a ggplot to object, or we call the ggplot function, even though we're using ggplot2, it's still we call it ggplot. So if we want to create something similar to what we created earlier, we'll just run this code, and then we'll start to break it down. All right, so you can already see, like, we're starting off just with something real basic and default. It already, to me, looks quite a bit nicer than the base plotting functions. And we'll go over this more down here, and there's more that you can read. But essentially, we're kind of initializing this plot. We're providing the data frame that we're using to get our data from. And then in this right here, we're providing what's called the aesthetics. And so all we're doing here is providing our value for X and our value for Y. So this corresponds to 2 columns within the data frame. So just a slightly different method than using the $sign. It's using, it's already looking inside of MPG, so it knows where to look, and it's going to grab these 2 different columns. So this right here that's highlighted will just initialize the plot. It's not going to plot anything until we add a layer. And we do that using the plus symbol and then specifying geom point. Geom point is the function that actually creates the scatter plot. And it inherits everything from the ggplot call. So it's getting what's a plot here, and the data set to use, and then it's actually what plots these points. Like I said, ggplot2 goes in layers, so we could even add additional layers to this, which we'll do later on in this topic. I think I covered. Oh, so there are geom point is called a geom function, and there are a lot of different ones of these. You can look them up. We'll be working mostly with geom point today for scatter plots. There are different mapping arguments for each one, but they'll take arguments from the main ggplot call. All right, so if we want to, let's go ahead and practice creating a ggplot. I'll give you a couple minutes to do this to get used to the syntax. If you want to, you can even just copy and paste the previous code and change the values that we're plotting. But I'll give you a minute to look at that. All right, so we'll start off with initializing our ggplot object. We need to tell it what we want to plot, provide the aesthetics. We'll say X equals, let's just do city versus highway, Y equals highway. So that initializes, we need to add the plus sign, then we can go down here and do geom point. Let's see if I remembered that correctly. All right, so now we've got this nice plot of what should be very correlated, the city mile per gallon versus the highway mile per gallon. Let's try this, just so we can see what happens. All right, so here, like I mentioned earlier, this actually just sets up the object. We do need that geom function, geom point. to actually plot the data. We can add, really modify the look of our plots by changing the values of those aesthetics. So the color or the size or even the shape of the points. So if we look up like the help page for geom point, we have these different aesthetics. So the ones in bold here, X and Y, are required. But we also have things like alpha, the color, fill, the shape, size, and stroke. So all of these are really going to affect how this looks. So if we run this, all right, so now we can see we're plotting here the a little bit differently, the displacement, the engine size, and the highway. Here we moved our aesthetics down to the geom point function. So the only thing it's inheriting from this ggplot is the data frame or the data set to look into. And so now we're calling in these aesthetics just the X and the Y, and then we're specifying here the color, which is going to be the outline color, the size, which is the overall size, the shape, which we'll cover more in a minute, the fill, which is red here, we can change that, and the stroke, which is the thickness of the outside. So if we want to change this, we can do purple, and if we want a lighter stroke, we'll do 1. All right, so now we can see that black band around each dot's gotten smaller. We've changed the inside of that color to purple. If we want to get crazy, we can do purple here. And I don't know, sky blue. There's all sorts of colors in R. All right, so we can modify this, in any way to change how our graph ends up looking. Are there any questions so far over just this ggplot and then changing kind of these different values in the geom point call? All right, nothing in chat. All right, well, we can move on then. I know this is the pattern of kind of inheritance and things can be a little tricky to figure out, but it is easy to modify once you have it set up. All right, so let's talk briefly about shapes. So here we specified shape as number 21. And that's just the standard number for a circle that can be filled in ggplot. So this right here is a nice infographic for all of the different shapes that are available in ggplot2. Something to note that only numbers 21 through 25 can take the stroke and the fill arguments. All right, so these other ones you can't modify how thick the border is, and you can't change the fill. All right, so we have another independent exercise. You can take a few minutes to do this and come up with something crazy. If you want to, you can even just copy and paste the code up above. And if you have something interesting, throw it in chat, and we'll take a look at it, play around, and just get a feel for what each of these different aesthetics does. Be an Aggie. All right. Any questions? Are we happy with that so far? Can we move on to the next section? All right. All right, so this is cool and all, and I mean, like, this looks kind of cool, honestly. I mean, I wouldn't, but you know, we could get it, the actual plot itself looking really nice with the size of the points that we want. And then we can start adding things like our X label and Y label. And you can see this is using the same arguments that the base plotting function is. So that is nice. Instead of main, though, we are using the GG title. And instead of providing it within like ggplot, again, we're having to add them in layer by layer. So we're adding our geom point here. That's just going to do displacement in the city. And then now we can start adding in like a title. And then we add in another layer, which is our x-axis label, and another label, which is our y-axis label. So if we run this code, now we can see this, you know, really clean looking graph that will have our title and our axis labels and everything like that. So if we wanted to, we could even, you know, combine this with the previous exercise and come up with, you know, a highly modified scatter plot. All right. So let's just go ahead and look at this together. I'm going to copy this to the clipboard. All right. Here we're setting up the ggplot2, the object, what we want to plot. Here is the where we can fill in how we want the points to look, and we're actually plotting the points here. So here the outer color is going to be black. We're going to use circle again. Here's our size, thin border. Let's change this to, I don't know, pink. And we've plotted all that. And then let's go ahead and do this. So I'm just commenting that code out, and we'll see what this does. And then we can go in and start adding each additional thing. So now we've added this. So we've added our title, but again, we need to go in and add another layer and so on. So just wanted to reiterate that. All right, so now we've got, this is something that, you know, is starting to look publication quality and ready, as opposed to those base plotting functions in R. We may also want to add plot labels to our plots. This is a large data set. So to go through using these two new geom functions, the geom text and geom label, I'm going to create a subset of our data using that subset function that we learned about in the data frame. So right here, I'm creating the data that we want to plot now to start to look at the geom text and the geom label. And I'm subsetting, looking for everything with a manual transmission. All right, so you know that's going to cut it down quite a bit, right? And then again, setting up the object, doing the scatter plot. It's inheriting everything from aesthetics and the data. And then the geom text, we're adding in another aesthetics call. And we're saying we want our label to equal the model. All right, and it knows it's going to inherit data from the ggplot object, so it knows to look for there for the label. So if we run this, all right, so now we've got something. Right? It's not great looking right now. It's to be frank, it's quite ugly. But we can see we've got no Altimas here, some Corvettes over here with very large engine sizes. a Mustang, some pickups. All right, so if we want to go in and clean this up, we can. We'll need to look at some of the arguments that ggplot and geomtext take to see if to see what we can adjust. So I think, yeah, we have plenty of time now. I'm kind of blowing through this, so we can take a couple minutes and come up with something. Look at the arguments for ggplot and geomtext and see if you can come up with a solution for cleaning this up a little bit. All right, I'm not going to cheat and look at the solution. I mean, it's been a while since I've done this, but I am going to cheat and copy this. And I did look up the help for geomtext. And let's see, aesthetic. Let's try nudge x equals 5. Let's just see what happens here. Have I misspelled? Oh, I didn't. There we go. All right. Oof. Okay. So I did nudge x equals 5, and it shifted everything over to the right quite a bit. I don't think that's what we want to do. We'll try nudge y, and we'll set that equal to 1. All right. So we're starting to look a little bit better here. We just nudged the labels up a little bit with that function. There's still some other things. It said look at xlim. Let's see, how do we do this? We'll do 0 to 8. Let's try this. Could not. No, there's no. Element must be a 2-element vector. All right, so xlim is going to change the range on our x-axis apparently from 0 to 8. And so let's play a little bit more with that. Let's say 1 to 8. We still have a lot of overlap here. I don't think we need to change the y lim because it looks pretty good to me. Going from what I guess probably 10 to 35. There is another function though. Let's try check overlap. I do remember this one. All right, so starting to look a little bit better. What we had to do is the check overlap is going to look for text that's overlapping and help prevent that. We lose some information, but it cleans it up quite a bit. Maybe if we do, let's try this, nudge y, -1. No, I didn't like that. All right, did anybody come up with something that looked better? Let's see what's in the solution. Yeah. All right, so and then obviously we can change our points and stuff too. And I just got logged out again. I'm not sure why this keeps happening. Okay. All right, we'll look into that on our end. It may just be something with the package itself. Okay. All right. All right. Not the end of the world, but it is annoying. All right. Where were we? All right. So the geom label function is very similar to the geom text function. Let's just look at the solution real quick. It's almost identical. It just has a slightly different appearance. And so now you can see the labels are in nice boxes. So that's the only real difference between those two geom functions, is the label versus the geom text is the output. And so I think this looks a bit cleaner. We could do check overlap here too. Oh, actually, I think that is the difference. I don't think you can do check overlap. Yeah, it doesn't have the check overlap option. But you know, if we could blow this up and spread it out more by changing the xlim and ylim. But those two methods allow us to add those labels if we want them. All right, I think let's move on to what I think is one of the cooler aspects of ggplot2 as far as like scatter plots go, and that's mapping different variables to different aesthetics. So here is some very simple code on how we can do that. It looks very similar to our very first plot with ggplot2, where we've got our MPG, that's our data frame, and then we're our X value and our Y value. But here we're saying we want this aesthetic, the color aesthetic, to be equal to class. All right, so class is the class of the vehicle itself. It's one of the columns in the MPG data frame. So now we have a lot more information that's present here just by mapping a third variable to one of these aesthetics. And so we can see that a subcompact car and a compact car are taking up these really small engine spaces with really great miles per gallon. And then if you get into things like SUVs and two-seaters, which if you remember, that was like the Corvettes and the Mustangs and things that are kind of the sports cars, those are going to have those higher displacement. And so we're presented with a lot more information here than just, you know, the downward trend we saw in miles per gallon over the size of the engine. And so I think this is a really cool thing. We can also, you know, explore other aspects, maybe like manufacturer or I can't remember off the top of my head what else is in MPG. So in this independent exercise, we're going to map another aesthetic to the variable plot, and we'll do X and Y as the displacement and city, and then we're going to add, again, the color, we're going to assign that to class, but the shape of the point we're going to assign to drive. So drive, I believe, yeah, it's front wheel, four-wheel drive, or rear wheel drive. All right, let's do this together. We're going to cheat. We're going to copy. All right, and then all we have to do here is set shape equals drive. All right, so now there may be too much information in this graph. But if you have, you know, something that needs to be examined with this many, you know, aspects or observations or whatever, you can map those to multiple different aesthetics, right? So the limit's not 2 or 3 or, you know, even 4. You can start looking at other things as well. And then you can go in and why I mentioned earlier that this can take, you know, several days or even, you know, weeks, is because there are just so many ways to modify the aesthetics and how they're mapped to the different variables and things like that. All right. Are there any questions on mapping variables to different aesthetics before we go on to adding even more layers to the plot? All right. All right, so the next geom function that we're going to look at is geom smooth. Let's just run this and have a look. All right, so it's the same graph we've been looking at, but now we've got this line that kind of estimates the mean and maybe dispersion around the mean, the confidence levels. And so at this point, like we could even, I mean, we're getting crazy, but you know, if you really wanted to start adding things. Oh my goodness. What did I do? Oh, okay. I broke it. That's good. We always like breaking things. So it's trying to do this over, it looks like each individual class. So that wasn't a good idea. We could figure out how to do this, but I can't imagine the type of deep dive that I would have to do. All right. So we'll just go back to this. All right. And then I think, the last thing is just an independent exercise showing how to modify the aesthetics within Geom Smooth. And we can just do that quickly together. It's really straightforward. Copy to clipboard. And so the only thing I've done is set this SE flag, that standard error, those confidence intervals, to false. And now we just have a straight line. So the whole point is to show, you know, how much you can modify and how ggplot2 builds in layers, and you can go in and heavily modify exactly what you're plotting. There's also geom histogram for making nicer histogram plots. There's all sorts of different geom functions. There's entire books written about data visualization in R, which I'm sure you're aware of. And that could be a whole nother, 6-hour course. But that was all that I was planning on covering today. Are there any questions over anything that we've covered so far? All right. Well, then with that, let me just pull this up and say that if you want any help with, you're on the ACES cluster now under our training allocation. So you can keep playing around with this workbook. You can do the bonus sections, or I would suggest downloading it if you want to have a more secure permanent copy. And then you can play with it on your own systems or your personal computer. If you want additional like kind of training material, maybe a thicker workbook with it's more fleshed out, I would be happy to provide that with you. Just send me an email and I can shoot it your way. We're always happy to share training materials with anybody. If you are if you work at a HPC center or something like that and would like to collaborate on these types of training sessions, we're happy to do so. If you have any questions in R and you've made it this far, I'd be happy to answer questions. You can just email in and I'll help if I can. I want to thank you guys for sticking by and sitting through this. I know it's grueling to do this much in essentially 5 hours, so I applaud you for your tenacity, and thank you all for participating. And I'll stick around if there are any questions. You can let me know. Otherwise, thank you all very much, and have a wonderful rest of the week.